This is Analysis and Redesign of Can Openers by Charles Newton, Liam Clayman, Adam Good, Connor Strang, and Matthew Rosolowski. Can openers remove the lid of the can. A circular blade is inserted into the top of the can and then moved around the top edge by a cranking handle that rotates a gear that rotates the can. It's designed to be able to fit on a variety of different sizes of cans, and the estimated production volume for primary and secondary consumers is around 750,000 units per year. Can openers remove the lid of the can. A circular blade is inserted into the top of the can and then moved around the top edge by a cranking handle that rotates a gear that rotates the can. It's designed to be able to fit on a variety of different sizes of cans, and the estimated production volume for primary and secondary consumers is around 750,000 units per year. The primary and secondary customers for can openers are households and commercial use, respectively. For households, can openers need to be able to open a wide variety of cans, need to be easy to use, safe and reliable, and their total volume is about 417,000 can openers per year. On the commercial side, restaurants, catering, etc., and food production use can openers. They need to be fast and durable as they're used many times a day quickly. They also need to be safe and reliable, and about 333,000 can openers are bought in the industry per year. Shown here is our FAST diagram. It shows the important function of a can opener being open containers with subfunctions branching off. Two subfunctions with more branches are remove lid and assure dependability. The first has branches which detail how different parts of the can opener are used to accomplish the subfunction. The second branches off with different ways of how to ensure it.
Here is an exploded view of the can opener we will be using. It shows all the parts, including the handles, gears, plates, and twisting handle configuration. Here are two possible assembly sequences for the can opener. The sequence on the left has nearly each part being assembled one at a time, while the right sequence has the opener being assembled in two parallel sequences before being riveted together in the final step. After comparing the two sequences in 5 different criteria, the second is revealed to be the superior sequence because of its ability to use assembly in parallel.
By taking the 10 functions from the FAST diagram and all of the parts from the can opener assembly, we were able to create the function component mapping matrix, which shows which parts are responsible for which functions.
This is the bill of materials and rough estimation of the total cost per can opener. For each part, we were able to break down the cost using methods and materials that were given in lecture, as well as some assumptions that had to be made. And then using these broken down costs, we were able to find the total unit cost per part and the total overall cost per can opener. This ended up being $22.73, which is relatively high and something that we can hopefully bring down.
After creating a bill of materials, we can then move to creating a quad chart, which plots the functional importance of a part over the mechanical and assembly cost of it. This allows us to see which parts need to be eliminated, redesigned, and left the same. From this, we can see that the right plate, the left plate, the twisting handle insert, and the blade spinning insert are both very functionally important, but also have a high manufacturing and assembly cost, so they need to be redesigned. You can also see that the rivet, plane washer, and head cross recess screw are both low manufacturing cost and low functional importance, so those can both be eliminated.
We took each of the 10 functions from the FAST diagram and compared them between our two consumer groups. We found that the biggest difference between our consumer groups was the speed and durability needed. In order to design for the higher speed and durability of the commercial use of the can opener, we created different modules for the twisting mechanisms between the household and commercial uses. The parts that are not in the rotating mechanisms are common between our two designs.
Here's the CAD for our product family design. On the top left, we have our primary consumers, and on the top right, we have our secondary consumers, where we have the handle made to be more durable and longer to apply more force and increase the speed while spinning the blades. To go with this, we also have made the blade larger and the can gripping gear larger. And in the bottom middle, we have the parts that are common between both designs. Here we have our modified assembly for our product family. In this, we have used assembly 2 and increased delayed differentiation in order to increase efficiency.
For automated assembly, the lower blade configuration was changed. The screws and washer were taken away in accordance with DFA Guidelines 1 and 2, and the shaft was changed to allow better orientation and for easy insertion of the rest of the components. After all 3 components are added onto the shaft in the new configuration, the shaft will be heated up and made into a rivet so the blade and gear can spin in place. Analysis was performed on the old configuration before changes and the new configuration after all DFA guidelines were considered. The new changes allowed the configuration only include 4 parts, remove the low importance fasteners, and achieve a 30% savings in the cost.
Here is the redesign of the blade for manual assembly, in which we have implemented DFA 1 to reduce the number of parts, DFA 2 to reduce the number of fasteners, and DFA 5 to reduce the variety among parts. Here we have the redesign of the right plate for manual assembly, in which we have implemented DFA 6 to increase symmetry, DFA 8 to avoid tangling, and DFA 10 to allow for easy insertion. Here are the tables that show the results for before and after our redesign for manual assembly. As you can see, the total time has greatly decreased from our redesign, as well as the assembly efficiency.
The first redesigned part is the blade. The key dimensions are shown on the part screenshot. The determined critical dimension is the gear dimensions with a tolerance of plus or minus 0.5 millimeters to ensure sufficient meshing between gears. Based on the process capabilities, we have decided that die casting, sheet forming, and machining will be potential manufacturing processes. However, we recommend die casting zinc aluminum alloy to reduce costs because of the large batch size. The second redesigned part is the left plate. The key dimensions are shown on the part screenshot. The determined critical dimension is the large hole with a tolerance of plus or minus 1 millimeter to ensure that the insert can go through the hole with a clearance fit. Based on the process capabilities, we have decided that sheet forming and machining will be potential manufacturing processes. However, we recommend sheet forming steel 304T to reduce costs because of the large batch size.
By using analytical methods, we were able to estimate the cost reduction of the right plate and our blade mechanism due to our improved design. We saw about a 7-cent reduction in the price of our right plate and a 60-cent reduction in price of our blade mechanism. For the right plate, we saw a slight difference between our analytical cost estimation and the estimation given by hubs. This is mainly due to differences in the material cost used on the site and what we were given in lecture, but both estimation methods still gave similar price reductions due to the improved manufacturability, even though the overall estimations were slightly different.
For our design of product system services, we have decided to go with an app-based platform sharing service. This included with a monthly subscription similar to the app Turo. Our idea is to put our own kitchen appliances on an app, and you are able to rent these appliances to your neighbors. This allows for customers to not have to buy every individual appliance, reducing costs to consumers, and with less appliances in circulation, we hope for a reduction in waste. In this final slide, you can see our original design versus our final modified design. As you can see, we have made significant changes in order to reduce cost and increase efficiency throughout the assembly process. This concludes our analysis and redesign of can openers, and we will now open the floor to questions.